Hi everyone, welcome back to the liquid recovery and natural gas processing engineering. We are talking about the straight refrigeration process, and this is a straight refrigeration process that we discussed in the previous lecture. Well, this straight refrigeration process has some different types. The configuration of the equipment is different in 4 different types, and some of them has different parts. So let's look at the variations in the installation and see which one is good for what purpose. Let's look at the type A. Here we are discussing. Uh, Here we are, first one. Now, this is the straight refrigeration process, but in this process, as you see that we have two heat exchangers. For example, the wet gas is going through first this heat exchanger, yeah. So first it is going through this heat exchanger here, okay, and this one. Then it is going through this one, and then we have the gas chiller. So first we cool the gas through the heat exchanger, this one, using this one, and then we send it through the gas chiller. Okay, then after it passes through the cold separator. Okay, in cold separator, gas chiller makes it very cool, and then in cold separator they separates. I mean the liquid is separated, goes down, and the gas goes up, and the liquid goes down. But when it passes through this one, again we cross it through the heat exchanger, and then it goes through like this here. Now in this fractionation, again you can say fractionator or you can say stabilizer. The liquid goes here, stabilize here, and then we send this product there. And if there is any gas, we cool it and we send it. We, if there are any still product, we then process them again here in this case. So that's the process of the type A that we are processing. So it is saying the same story here. In the type A, the gas is cooled against the residue gas and cold separator liquid before being chilled. So gas is cooled before sending to the separator. So we are cooling the gas using these two heat exchangers here before sending it to the gas chiller. This is the first statement. And then it is using the top feed fractionator, okay, and overhead being recompressed and recycling inlet. So it is using this fractionator which has top part, which if there is any wet gas, again it goes through back again here in order to remove them further, and whatever product we have, we send it here. So if it has any gas, it goes back, inlet gas, so it goes back here. So they process it again from this fractionator, and the liquid, which is 100% liquid, it goes down through here. This is the second statement. Use of liquid feed gas exchanger helps reduce the chiller load. So we are using these two heat exchangers to reduce the chiller load. Otherwise, we have to put a very powerful chiller. So in order to save some energy and reduce the load on this gas chiller, we use these heat exchanger, which helps us to reduce the cost of electricity and the energy. And then the dew point is achieved in the cold separator, and where both are separated, as I said, the cold separator operating condition, and both are separated here in this case. Okay, now, okay, this is a low separator pressure around 600 psig, and can be used below C3. I mean, can be used for leaner gases, and include ethane recovery in this case. Now in the next step, now this is type B. In this case, we have some differences. In this one, from the cold separator, it does not go to the heat exchanger. In the previous one, in the previous example, this was going through the heat exchanger. Then we were sending to this one, but not anymore. Now, yeah, now from here it goes directly to the here. Now, so this is the difference between this. Again, the same. If there is any gas with some liquids, it's recovered and sent back here, and the liquids, the products directly go to the product. This is the type B. Okay, type B. also use a top feed fractionator, but the cold separator liquid is fed directly to the fractionator. As I said, from the cold separator it goes directly to the fractionator. Okay, and now, yeah, this is done when we don't need to put it through the heat exchanger to cool it further or to change the temperature of it. We just directly, the fractionator and cold separator, their temperatures are compatible, and we are sending from cold separator to the fractionator directly without any problem. Okay. Then we have the type C. In the type C, we have a special part. Okay, this is the special part here. In the type A and type B was not there. In this one is the most uh, uh, efficient one, you can say. In this one, what we are doing, again, we have the inlet gas. We are passing through the heat exchanger one. Okay, and it goes through then gas chiller, cold separator. Again, it goes to the heat exchanger, as we say, goes there, and then it goes to this tower. But in the previous case, this was directly going through the here. Okay, there was no separate equipment here, but we were sending directly this to the inlet gas so that it process again. But in this case, no, we have an accumulator, and the accumulator process this. It has the same function like this tower, but it accumulates any more liquids, and these liquids are then sent back to this tower. So in this one, yeah, so in this tower, it is accumulated, liquids are accumulated down and goes back here, and the gas goes back, the residue gases goes back like this. So that's the difference. So this is the most efficient one, and it saves a lot of time, because in the previous case it has to go through all the process again, but here, using the accumulator, it saves the increases the capacity of this plant. At the same time, it decreases the operating cost of the plant at the same time. So it has the highest liquid recovery efficiency and higher cost due to the overhead system. So initial cost is higher, but in the operating cost, you will save a lot of time, and your capacity can be increased in this one. Well, in this case, any combination can be used. Sometime higher separator pressure, richer gas, richer limited to propane plus. So, but C is the most efficient one, as you see, and is the time-saving one in this one. In this one, again, we have a fractionator feed pump. We are giving it a pressure here. So here the special part is that it has the pump here, feed pump. So again it goes through the heat exchangers, then chiller, then cold gas, then again heat exchange, pressurized this time, and using the pressure again we are sending it back here, and the product is going there. Okay, from the cold separator also gas is going in this direction outside. So that's the type D. These are the 4 different type of refrigeration that are used to remove this uh, liquid hydrocarbon from the gas stream. Yes. When we talk about the liquid recovery, in order to have a good efficiency of removing the liquid, we need a stabilization system. Whatever if you are using the JT based LTA system or the mechanical refrigeration that we talk about, but the stabilization tower like this one is very good, because we reduce the pressure, and based on the reduction of pressure, it is very good. It after some time all the gas will come out, uh, and the liquid will be separated from it. So liquid must be stabilized by flushing to lower pressure or use of the stabilization column, and this will increase the efficiency of the system. Now, okay, and the stabilization column can produce high quality and better controlled product, as I said. So after stabilization, the product is cooled and sent to storage and so on. Now, this is what we are talking about, the LTS and the straight refrigeration system. They are mostly related with the propane plus recovery. Now, what if you want to recover the bit heavier gas, than denser gas than the methane, which is called ethane, and how we can remove it? So what we said, that the mechanical refrigeration and the dew point control, mostly they are used for the propane based recoveries. Okay, and high propane recoveries, and now we are talking about ethane plus recovery, ethane, and of course the cryogenic temperatures are needed. We have to keep minus 50 degree Fahrenheit and less in order to achieve the better ethane plus recovery and so on. As you know that, as you can see that if we keep the pressure around 100 to 200, we can achieve a very low temperature, which can be used to remove the ethane recovery. Now, in order to remove the ethane, we have three processes. One of them is JT expansion, another one is the turbo expander, and third one the mechanical refrigeration. These are the equipments which has no moving part, this JT expansion and turbo expander. These are used for the ethane recovery process, and I will show you how both of them are used to use the chill the gas and to remove this ethane plus products out of it. Okay, and what is the difference between the JT design and turbo expander? The gas expansion is adiabatic across the valve and nearly isentropic. The JT design tends to be less efficient per unit than the turbo expander. Nowadays, mostly industry, especially in Dana gas, also they are using this turbo expander in order to remove the liquefied petroleum gas. They have their turbo expander. Okay, so and when we talk about the adiabatic, it means that no heat transfer from the surrounding or environment to the inside. So it is completely isolated system, and no outside environment is affecting the temperature of the gas inside. That's why the turbo expanders are more efficient in this case. So now I will show you the videos for both, and then we talk about this further.
Is something that can negatively impact your oil and gas production. Discovered by British physicists in the 19th century, the JT effect states that when the pressure of a gas changes, its temperature also changes. In natural gas production, this means that when gas pressure is reduced across a control valve or regulator, its temperature is also reduced. Because all gas carries some element of moisture in it, this can present a potential freezing issue when the temperature of your gas line drops below 32 degrees Fahrenheit. According to the Joule-Thomson effect, a 100 psi pressure drop results in a temperature drop of 6 to 8 degrees Fahrenheit. For example, if you're cutting the gas pressure from 900 to 200 psi across a control valve, the temperature of the gas would drop approximately 42 to 56 degrees. To prevent freezing, operators sometimes wrap insulation and heat tape around their valve. This method presents a challenge when they need to check or repair the valve. A good alternative is a gas catalytic heater. This heater uses supply gas to provide a flameless, radiant heat that keeps your valve above freezing temperatures. The design allows operators easy access for maintenance or repair. The surface of the heater reaches a maximum of approximately 800 degrees Fahrenheit and is approved for hazardous environments. For more information about catalytic heaters or any other Kimray product,
this is Joule-Thomson effect. It states that when a highly compressed gas is suddenly allowed to expand, it causes cooling. Do you know that the machineries today, like the AC refrigerators, use the compressors in order to get more drop in temperature by applying the Joule-Thomson effect? So let's discuss the mechanism of the Joule-Thomson effect. As you can see here in a diagram that the gas molecules are passed from a high pressure region to the low pressure region through a porous material. So allowed to pass through this increase in the kinetic energy of the molecules. So change into the liquid state. Most methods of the liquefaction of the gases based on the Joule-Thomson effect. Some important methods for the liquefaction of the gases are: number 1, Faraday's method. In this method, the cooling is produced by using a freezing mixture of the ice and the various salt. The gases like the sulfur dioxide, carbon dioxide and the chlorine etc. can be liquefied by this method under their own pressure. The second important method for the liquefaction of the gases is Lind's method. In this method, cooling is produced by free and sudden expansion of the compressed gas into a low pressure region through a small nozzle repeatedly. Thus, ultimately, they get liquefied.
So basically
As you can see here in a diagram that the fresh air enters to the compressor where the gas is highly compressed.
So this is the JT valve, and first when we want to use the JT process, I mean Joule-Thomson valve, as you saw before, it should not have any water. So what we do when we have a feed gas, it must be dehydrated, and we have to remove the water vapors. And then we, in order to reduce the temperature, we use this heat exchangers, and then we use a chiller, and the chiller actually cools it further. And then we have the cold separator. From the cold separator, when it goes inside the deethanizer, here are the JT valves. So we have, in this process we have two JT valves here. One is this one, another is this one. Purpose is to to remove this ethane plus products. So in this time the ethane is removed and the liquids are sent down, and the ethane is then sent up like this one. This is the process. This is again the air cooler. This is air cooler. This is chiller. This is heat exchanger. And then if we these are for the dehydration process. In order to, if we have any products, so that's the process of the JT process that is used to remove the ethane plus recovery. Then we have another process which is the thermo expander. Nowadays wherever we are using the ethane plus recovery, ethane turbo expander are mostly used. These are the rotary ways, as I showed you in the video also. So in this case we have uh, after we, this is the feed gas, goes through the heat exchanger here, and then we have the cold separator. After the cold separator we put the turbo expander here, and based on the turbo expander we remove the demethanizer or deethanizer. We get our product, okay, through the, and it control its temperature, and we send it to further to the process. So this gas exchanger is actually, it has the refrigerant, okay, it's very cool, okay, and we reduce the temperature, we make it very cool. Then we send it to the cold separator. In cold separator, two products we get. One of them is the liquid, which we process using this uh, the Joule-Thomson valve, propane plus. And for ethane plus we use here the turbo expander, where both of them are separated here uh, further. So the ethane plus products goes from here, and the liquids then goes from here. So these are the products for the turbo expander process. So that's all about the JT valve, turbo expander, and simple refrigeration process, and hope to see you in another lecture soon.